Hi, my name is Berkay and here I am in another video. In this video, I will going to explain you what a UART is and I will going to show you an UART demonstration by using Vivado. So UART means Universal Asynchronous Receive and Transmit, and it's a hardware communication protocol, and it is the most common device-to-device communication protocol in the world. Now, asynchronous means we don't use clock signal to regulate the transmitted data. And this is the simulation of a UART transmission. I will going to explain what is happening in this simulation, but first I need to show you the frame format of my UART. This is the frame format of my design UART. And as you can see, it is a four state. One is the idle state, and next one is the start state, this one is the data, and this last one is the stop state. In either state, this is where basically our UART is resting. It only receives the logic high signal, and while receiving this logic high signal, it knows that there is no data transmission is happening. But when that logic high signal drops to logic 0, and at that moment you ought to understand that data transmission is about to start, so it will going to ready itself in the start state, and it will going to wait in this start state for a t amount of time, and t is equal to 1 divided by baud rate. You might ask what a baud rate is, and it basically is number of bits that can be transmitted in a single second. So 1 divided by baud rate is equal to amount of time that needed to transmit 1 bit. So in the start state, our UART will going to wait for a 1 bit worth of time, and after that it will go to the data state, and in the data state we will going to start to transmit our bits, and for every bits we will going to wait for t amount of time, and after all the 8 bits is transmitted we will go to the stop state, and we will wait in here for a generating amount of time, and after that lastly we will go to the idle state again. Now my UART is a literary, so it will going to send the least significant bit first, and the last bit it it will send will be the most significant bit. Now for the receiver part, it's a little bit different, because in a perfect world, in a simulation, transition between logic high and logic low happens simultaneously. But real world is not like that. There will be a time delay between logic high to logic low, so we need to be sure that we are receiving the correct data from another device. So we will going to start our reading in the middle of the transmission. We will wait for half of t amount of time, and we will go to read our data in the middle of the transmission. We will going to wait t amount of time, and after the t amount of time, and after t amount of time onto the stop state. And this way we will going to be sure that we are receiving the correct data from another computer or device. Now I will going to show you my code in Vivado and the simulation. So after explaining you what a UART is and showing you the frame format of my project, now I need you to show VHDL design of my project. Now VHDL means very fast hardware description language. So what it basically does is it will going to explain what the hardware in FPGA board is going to do. So this is the entity part of my project, and this is the architecture part of my project. And as you can see, entity is just inputs and outputs and generic values, and architecture is what going going on inside an UART module. And now let's start. First, I have a clock frequency and it's equal to 100 million hertz, and this is the baud rate. So as I told you in the frame format, and baud rate is number of bits that can be transmitted in a single second, and this is the stop bit and it's equal to 1, and this means that you are going to use 1 bit for a stop process, and this is the port side of my UART module. And as you can see, it has a clock for input, a transmission static, a data input, and receiver input. And this is the data out and receiver daunting. When the receiving process going to end, it will going to send a 1, and this is the transmission daunting, and it is the same thing as the receiver daunting. It will going to send a 1 when the transmission process ended. And now this is the architecture part of my project, and as you can see, I have created state, and this is the transmitter state, and this is the receiver state. And as you can see, it has a transmission idle, transmission start, transmission data, and transmission stop substates. And my first state in the transmission will be a transmission idle. It will going to wait in here, and I have done the same thing for the receiving state. And I have created some constants, and this is the bit timer limit, and it's equal to clock frequency divided by baud rate. And this basically means that this will going to give me the right amount time for the transmit one required time for transmit one of my bits. And this is the heartbeat timer limit, and I will going to use it in the receiver process, because as I told you in the frame format, I will going to read my data in the half point of a transmission, because in that state I am a little bit more sure that my data is in its correct form in the half point of the transmission. This is just bit timer for transmission state and bit timer for receiver state. This is just a buffer for our data in. And now let's start our transmission process and receiver process. Now in the transmission process, this is process that assigns the clock. Whenever the clock changes, this process will be triggered, and first thing it will going to check is if it's the rising edge of clock, and if it is, it will going to check if transmission static input is equal to 0 or 1. If it is equal to 0, it will going to stay in the idle state, and if it is not, it will just going to start the bit timer and in here. And after that, this is our case and when statement, and in this case and when statements I have assigned some parameters to my states, and in here either state we are just sending a transmission output as always 1. Also we are sending transmission daunting output as logic 0, and after that we were going to check if our transmission static is 1 or not. If it is 1, then we know that a transmission is about to happen. So we're going to assign our data input to a transmission buffer. And after that, we were going to send a logic 0. And lastly, we will go to the start state. And in the start state, we were going to wait for a 1 bit amount of time. Bit timer is when bit timer ticks will be equal to bit timer limit minus 1. It will going to reset our bit timer and it will go to the data state. You might ask why there is a minus 1 in here, because our counter starts from 0, so we must add a minus 1. Now in the data state, we will take the least significant bit in our buffer signal and we will send it as a transmission output signal. Then we will going to wait for a 1 bit and we will going to increase our bit counter by 1. And after that we will going to do that again and again and again until we reach the 7th bit or most significant bit. And after that we were going to reset our bit timer and we will send a logic high from our TX output. Then we will go to the stop state, and in the stop state we were going to wait for a 1 bit amount of time and we will increase our bit counter by 1 and we will check if our bit counter is equal to 7 plus our generic value of stop bit. With this generic value you can change your stop bit length. It can be 2, it can be 1, there is no problem. And after that we were going to reset everything and we were just going to send a transmission damping as a 1 and we will go back to the idle state. In the receiver process, it is not that much different, but there are some minor differences in here. And as you can see in here, it will going to first check if it's a rising edge of crack, and if it is a rising of crack, it will check if receiving input signal is logic 1 and is bit timer equal to 0. And if it is, it will just stay in the idle state. But if it is not, it will going to start our bit timer. And this is the case 1 statement. In the idle state, we are just sending receiver damping output as a logic 0. And we are checking if our receiver input signal is 0. And if it is 0, okay, a data transmission is happening. We will go to the start state. And in the start state, we were just going to wait for half byte timer limit, because as I told you, we need to wait for half bit timer for to receive the most correct form of our transmitted signal. And after that we will go to the RX data state, and in the RX data state we were going to take the incoming signal and we were going to assign it to the least significant bit part of our data out. And after that we were going to wait 1 byte of a time and we were going to assign half bit time limit. And after that we were just going to increase our bit counter by 1 and we were going to do that again and again and again and again. That will be no problem. And then we will go to the stop state. Then in the stop state we will just going to wait a 1 bit timer limit, and after that we will just going to reset everything and we will go back to idle state. In this UART demonstration file, I have connected two UART modules that I have coded with each other, and we were going to simulate the data communication between each other. Now I have declared some generic and port values in here, and after that I have declared a component, and it's my UART component, and this is its ports and generic values. Now these are just some signals, and you can think them as wires that connects my UARTs with each other. And I have done a component initialization in here and in here. These are its generic maps, and clock frequency is goes to clock frequency, and RX statics goes to RX statics 1, and this is it. And after that, I have connected my UARTs transmission port to other UARTs receiver port, and I have done the same thing for the other UART. Now you can do this process in a data process, but this is really unnecessary because VHDL we're going to assign a flip-flop for this process, and it is really worth of time, not worth of time. And in this section, you are demo test bench VHDL file. I have simulated my demonstration, and in here I have created two constant, and these are the signals I am going to communicate. I'm going to transmit and receive with my UARTs, and in here this is my clock stimulus. Because of my clock frequency is 100 megahertz, I need to do a clock signal that corresponds to that value, and 100 megahertz means my period is 10 nanoseconds. So if it's the 10 nanoseconds, 1 nanosecond should be logic high and 1 nanosecond should be logic low. So this is what's happening in here. And this is just my data students process, and I was just going to send my data 1 in, it's 76, and data 2 in, it's data AC. Now before the simulation, I want you to see this. This is all the code I have done in this VHDL project, and as you can see, this is my first UART and this is my second UART. Data 1 in is coming in, and after that it will going to transmit it by bit to another UART, and data 2 out will be our data 1 in, and same thing will going to happen for my UART2. Data 2 in will come in here, and it will going to transmit it to my UART1, and data 1 out will be data 2 in. But let's see this, and this is all the code I have done in the UART module, and you can see the so much of lookup tables and flip-flops in this one UART module, and you can see the multiplexers, register, flip-flops, and like I said, VHDL simulates a hardware, how a hardware is going to do what it must do, and this is what VHDL are going to do. It will going to simulate the hardware. Now we can run our simulation. Okay, I will just going to end my simulation in here, and as you can see, my simulation ended in here. Now let's see, let's do the full view. Okay, now this is the main part, and this two is the UART1 and UART2, and you can see that data 1 out and data 2 out is unknown at the moment, but when the transmission done tick is 1, they are both in the correct form, and as you can see, data 1 in is 76 and data 2 out is 76, and data 2 in is AC and data 1 out is AC. But I need you to show this. Now in here, as you can see, in the beginning we are in the transmission start process, and it will going to send 1 bit of worth of time of 0, and as you can see, 0 takes transmission out is 0, and after that it will going to send the least significant bit, and as you can see in here, it's 0, then it's 1, 1, then it will going to send 0 again, then 1, 1, 1, and last bit, the most significant bit, is 0. And after that, as you can see in here, it waited a 1 bit worth of time in the stop state, and the transmission has ended. It will going to do the same thing for the RX state, and it will just going to wait a half of a time in the RX state, and it will just going to receive all of the bits in the half time bit limit, and after that, and after that, and after that, it will going to AC when the RX down tick will be 1. Okay, now this is how a UART is working, and you saw the and you experience the how a two UART model is communication with each other. And this is it. Thank you for listening to me.